In this video, we will be discussing the states of matter, as well as how we can classify matter based on the atoms that make it up. Before we talk about the various states of matter, we should first discuss what matter is made of. Atoms are the smallest unit of matter. They cannot be subdivided through chemical processes. They are often considered the building blocks of all matter. When we take two or more atoms and bind them together through the sharing of electrons via a chemical bond, we call that a molecule. The atoms in a molecule can either be the same type of atoms or they can be different. In the case of a water molecules are made up of one oxygen atom and two hydrogen atoms. If all of the atoms that make up a molecule are the same, we call that an element. The term element itself can be a bit confusing. It can either refer to individual atoms or molecules, but in either case, all the atoms that are comprising either the individual atom or the molecules have to be of the same type of atom. So for example, we could have an individual hydrogen atom, we would call that elemental. So for example, we could have an individual hydrogen atom, which we would call hydrogen, or we could have H2, two hydrogen atoms bound together to form a hydrogen molecule, which we would call elemental hydrogen, which is in the form H2. Now, when we're combining things together, we can have mixtures. That is when you have a combination of two or more types of molecules in a container. And we will get into how we can do the classification of each one of these and the different types of mixtures in just a little bit. Now that we've talked about what matter is made of, we'll look at the different states that we can find it in. There are four classical states of matter: solid, liquid, gas, and plasma. The first three are the ones we will be primarily concerning ourselves with in this course. Solids are when the particles, either atoms or molecules, are tightly packed in fixed space. The atoms themselves vibrate, they can move back and forth, but they do not move position, they do not shift position around. Liquids are tightly packed, but not in fixed space. So the atoms in a liquid are able to slide past each other. So the atoms can vibrate and they can move. In gases, particles are widely spaced and allowed to move freely within a container. Plasmas are the last type of classical state of matter. They don't normally exist on Earth. They are produced through extreme heat or ionization. The gaseous state of a plasma involves high electrical conductivity and comprises of unbound positive and negative particles. Plasmas are typically found in stars as well as neon signs and plasma TVs. On Earth, we can produce plasmas through putting a fairly large voltage through gas at low pressure, which is the case of both neon signs and plasma TVs. Now, there are many different non-classical states that we will not get into. Some examples of these are Bose-Einstein condensates, superfluids, dropletons, which were discovered just recently in 2017, as well as some theoretical states, such as those that you would find in black holes or very, very high temperature situations in the cosmos. We will now go through our three primary states of matter in greater detail. For solids, in solid matter, atoms or molecules are packed close to each other in fixed locations. The molecules themselves are able to shift back and forth a little bit, but they do not slide past each other. So although the atoms and molecules in a solid vibrate, they do not move around. They are held closely together via strong intermolecular forces. Typically, solids occur at lower temperatures, and that's because temperature is a measure of the kinetic energy of the atoms or molecules. If they have a lower temperature, they don't have sufficient kinetic energy to break the intermolecular forces that are holding them in place. Because of this, they have a fixed volume and rigid shape. So because the atoms themselves are not able to move past each other, their volume does not change. They also have a rigid shape because the atoms, again, don't move other than vibrating back and forth in their local position. Examples of solids are ice, aluminum, and diamonds, things that you would see in everyday usage. In liquid matter, atoms or molecules are again packed closely together, generally as closely as they are in solids. But they are free to move relative to each other. So the liquids themselves have a fixed volume because they are continuously touching each other, but they do not have a fixed shape. The difference between liquids and solids is liquids have sufficient kinetic energy, being that they are generally at a higher temperature, to temporarily break the intermolecular forces that are holding them in place. So they can break the intermolecular force that is causing them to touch another atom, moving in location and forming a new intermolecular force. So they have enough kinetic energy to break local intermolecular forces so long as they form new intermolecular forces in their next nearest neighbor. This allows them to slide past each other while maintaining contact between the various atoms or molecules. So because of this, because they must maintain contact, they have a fixed volume. But because they are able to slide past each other, they do not have a fixed shape. Because of this, liquids have the ability to flow past each other, making them assume the shape of their container. Examples of this would be water, alcohol, and gasoline. These are all substances that are liquids at room temperature. The last state of matter that we will be considering is a gas. So in gaseous matter, atoms or molecules have a lot of space between them. They are free to move in three-dimensional space. They are typically moving very fast, bouncing off one another. Because they are free to move between one another, they do not have a fixed volume or a fixed shape. Instead, they will fill their container. Now, one of the key differences between gases and solids and liquids is that gases are compressible. Because they have sufficient kinetic energy to break the intermolecular forces between the atoms, they are able to spread out and take up the entire volume of the container. They do not need to be in contact with each other. Because they are able to move around in that three-dimensional container, there's a lot of empty space between them. In the case of gases, what you can then do is put a force down on the top of the container, forcing the gases to occupy less volume than they otherwise normally would. This is what is called compression. So because gases are able to be compressed, they are compressible. In the case of solids and liquids, they are not compressible, and that's because they're already touching each other, so there's no excess volume. So if you push down on top of a solid or a liquid, the top of the container is not really going to move much at all, if any. In addition to the physical form that we find matter in, matter can also be classified based on its composition. So if we have some matter that we want to classify, we can ask ourselves several questions. The first is there only one type of particle in the container? If the answer is yes, then it is a pure substance. So in the case of a pure substance, all the atoms, if it is individual atoms, or molecules, if it is in like a molecular form, they're all the same. So we would call that a pure substance. If they are not all the same, then we will call it a mixture. Going down the pure substance route, so all the particles, molecules or atoms in our container are the exact same. We then ask ourselves, is it separable into simpler substances? If not, we would call it an element. So by that, we mean that all the atoms involved, are they all the same? If they are all the same, then we call it an element. If there is a difference in the different types of atoms that make up the particles or molecules, then we would call it a compound. So an example of elements would be helium atoms or hydrogen atoms. Hydrogen atoms, again, typically come in the form of H2. So helium atoms, hydrogen atoms, as long as the molecules themselves are comprised of all the same type of atom. So all helium, all hydrogen, all oxygen, as long as there is no difference in the type of atom that is making up your molecule, we can call that an element. On the other hand, if there are different types of atoms that make up the molecule, we will call that a compound. So water is an example of a compound. It is comprised of hydrogen and oxygen. So you have different types of atoms that make it up. Going down our other route, let's say our container has multiple different types of molecules. We would call that a mixture. We then need to determine, is the mixture uniform throughout? So if it is yes, we call that a homogeneous mixture. If it is not, it is a heterogeneous mixture. In the case of homogeneous mixture, an example would be tea. So if we're looking at tea, down on the atomic level, what we would see is you have some water molecules, you might have some sugar if it is sweetened. You'd also have the different flavonoids, the things that give it its particular flavor. If it is well stirred, then no matter where you take a sample out of, you will have the same ratio of water molecules to sugar molecules to flavor compounds. So the key to a homogeneous mixture is that it is so well mixed that no matter where you pull your sample from, you will have the same composition. You will have the same ratio of the different subcomponents, water, sugar, and flavor compounds. In the case of a heterogeneous solution, for these, your mixture is not well mixed, which means that depending on where you're pulling the sample from, you'll get different concentrations. An example of this would be wet sand. So if you're looking down on the atomic scale at wet sand, you would have your silicon dioxide that's making up your sand, as well as water molecules. Depending on where you pull the sample from, you'll have different ratios of the silicon dioxide, the sand, to water. And so this means that depending on where you're pulling your sample, you're going to get different ratios of water to sand. Another example would be something like iced tea. So if you have the tea itself, which without the ice might be a homogeneous mixture, but once you put different components like ice in there, depending on where you're pulling your sample from, you might get large quantities of ice and little quantities of tea, and so the water to sugar ratio would be different depending on where you're pulling your sample. Going into greater detail or more precision on what we mean by the various states or various classifications, we could have a pure substance. That is one that is made from only one compound. This can be either an element if all the atoms or molecules are comprised of the same type of atom. So we could think of helium or hydrogen gas or oxygen or nitrogen gas, as long as all the elements or all the atoms are comprised of the same type. We could have compounds in which the substance is comprised of two or more types of atoms in definite fixed proportions. So an example of that could be water, H2O, or methane, CH4. As long as every single molecule in our container is the same, we call it a pure substance. If they are different, then we would call that a mixture. So a mixture is made of two or more different components. If it is well mixed, such that no matter where we take the sample from, the concentrations of our various components are going to be the same, where for that your substance is generally going to be in the same phase, we could call that a homogeneous mixture. In the case where, depending on where you pull the sample from, you will get different concentrations, we would call that a heterogeneous mixture. A good indicator that you're working with a heterogeneous mixture is that you're working with something that has two or more phases. So you could be thinking of wet sand, where you have water and sand. The sand is a solid, the water is a liquid, and so you have both a solid phase and a liquid phase. Or in the case of like iced tea, you have ice, which is a solid, and then the tea, which is a liquid solution.